So in this video we're going to discuss and derive the law of cosines. So in our previous set of videos on the law of sines, the idea was that we needed tools to deal with oblique triangles. And what we saw was that the law of sines could deal with angle side side triangles, for example, could deal with angle side angle triangles, but we discovered that for side angle side and side 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 triangles, the law of sines wasn't a tool that was useful. So we wanted to develop a law that will allow us to deal with those two situations, and the law that we're going to come up with is the law of cosines. So before we show the derivation of it, we just want to discuss the law of cosines a little bit. So this is for a triangle labeled the way that we've been labeling them the last few videos, where we label the angles with capital A, B, and C, and label the sides opposite at each angle with the corresponding small letter, little a, little b, little c. And so when you look at the law of cosines, what you're going to see is that in each case you have an angle, and then you have the side opposite the angle showing in the leftmost position. So here's angle A, the side opposite A. Angle B, side opposite B. Angle C, side opposite C. So in each case, the side that's been isolated on the left side of the equality sign is the side that is opposite the angle that's being fed into the cosine function. So that's the first thing that you want to notice. The side that's been isolated on the left side, the other two sides show up on the right hand side. And what we want to notice next is that this piece right here, this a squared equals b squared plus c squared, or b squared equals a squared plus c squared, etc., looks like the Pythagorean theorem. So if we let ourselves have a triangle that isn't oblique, that is a right triangle, and we label, for example, A for the right angle, then little a is going to be the side opposite it, and it's going to be the hypotenuse of that right triangle. And a is going to equal 90 degrees. And when we plug 90 degrees into the cosine function, the cosine of 90 is 0. We get 0 times this stuff. And indeed, the law of cosines in the case where the angle A is a 90-degree angle does just simplify to the Pythagorean theorem. So there's a sense in which we could say that the law of cosines, or that the Pythagorean theorem, is just a special case of the law of cosines. There is an alternate formulation that you'll see in some textbooks where you just say, hey, let S sub 1, S sub 2, S sub 3 be sides on a triangle that has an angle theta, and let S sub 3 be the side that is opposite theta. And then you get this formulation. The side opposite the angle, is squared, and it equals the sum of the squares of the other two sides, minus 2 times side 1, side 2 cosine theta. So it has the same form. We just don't need to label the triangle with ABC. This would be a formulation we would use if we knew any of the three angles. It's kind of a more generic, almost a nicer way to do it. If you know theta, then S sub 3 is just the side opposite theta, and S sub 1 and S sub 2 can be the other two sides, and it doesn't matter how they're labeled. So the next thing we want to do is make sure we understand why this works for side angle side and side side side. So in the case of side angle side, for example, if I know side angle side, so let's say I know angle A, and I know the two sides adjacent A, so this would be usually A, B, C, so this would be little c, little b. Let's suppose I know little b, little c, I know these two sides, and I know the included angle, side, angle, side. That means I don't know the side opposite A. I don't know what little a is. And what you can see is, using this formulation directly, we would be able to solve for A, because we could plug in our values for B and C, and we could plug in the angle A that we know. We could simplify this and then take the square root of both sides to find the length, and we would take the positive square root because a length is going to be a positive value, not a negative value. So it directly solves the side angle side case. And if we think about the case where we don't know one of the angles, but we do know all three sides, B, C, and little a, or if we're using this formulation, S1, S2, S3, let's say we know all three sides, S1, S2, S3, we can just solve this equation for theta and figure out what theta is. So as long as theta is the angle opposite S3, we can solve for it. And this is just a matter of labeling. So if we start with S sub 3 squared equaling S sub 1 squared plus S sub 2 squared minus 2 times the product of side 1 and side 2 times the cosine of the angle theta that's opposite side 3. We could just solve it for theta. We could subtract side 1 squared plus side 2 squared from both sides, so we'd get side 3 squared minus side 1 squared minus side 3 squared, which would leave us with the minus 2 side 1 side 2 cosine theta, and then just divide both sides by minus 2 side 1 side 2. Divide by negative 2 times side 1 side 2, and this is going to equal 1. And that isolates the cosine of theta, and then we would just take the cosine inverse of both sides. And we take the cosine inverse of this side, which would dig the theta out of there, and we could solve for theta. So in this case, as long as the side you put here is the side opposite the angle you're interested in solving for, you can solve for theta. So if we know three sides, side, 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 we can get each angle we want by putting the side opposite the angle we want in this position and the other two sides in the other positions. So the task now is to derive the law of cosines. And there's going to be two possibilities. One possibility is that we have an acute triangle for our oblique triangle. So this is just like law of sines. We had two cases. We had to derive the law of sines for the case where we had an acute triangle, and then we had to derive the law of sines separately for the case where we had an obtuse triangle. So we had an obtuse angle sitting there, and that will be the case again. So what I'm going to do is derive it for the acute case where we have a triangle A, B, C with little a, little b, little c, and then you're going to get to do it for the case where you know an angle theta and the side 3 opposite of theta is what you want to isolate, and you're forced to drop a perpendicular on the sideline to the triangle that lands exterior to the obtuse triangle. With the law of cosines on the acute triangle case, everything can be done by dropping perpendiculars, but all of the perpendiculars land on the interior of the triangle. So the way that we have to do it for the case where we're working with an obtuse angle is a little bit different, and it needs to be derived separately. So that's going to be a homework exercise. It's going to be, hey, if you know the obtuse angle theta and you want to isolate side 3 squared, how do you do that? In the acute triangle case, here's how this plays out. Let's get rid of this mess and redraw it. So the derivation for the acute triangle case, which means we are going to need to drop a perpendicular on the interior of this triangle, A, B, C, little a, little b, little c. For the obtuse triangle case, we can get a couple of the law of cosines proven by dropping an interior perpendicular, but we're always forced to drop one on the outside as well. So for the acute triangle case, pick any of the three angles. It doesn't matter which one that you do. There's three of these that we want to verify. I'm going to verify this first one, and then the way that you verify the other two is just the same process. So once we have done one, we're going to say without loss of generality, do the same thing and you would get the other two laws. The process would be identical. But I'm going to do the one where I want to get a squared isolated on the left, and I have the angle A that's opposite of A. So I'm going to do it from that perspective. So the way this would play out is I would drop the perpendicular from C to the side line AB on the triangle. So I get two right triangles here. And then I'm going to go ahead and give this distance a name. This is the base of this right triangle. I'm going to call it X. And if that is X, then this distance right here is going to be C minus X, because C is the length all the way across the base of this triangle. And then what I can do is use the Pythagorean theorem. I can say if I labeled this as the height, because it's a perpendicular, I can say the Pythagorean theorem says that the sum of the squares of the sides equal the square of the hypotenuse. It's going to be x squared plus h squared equals b squared. X squared plus h squared equals b squared. And then I have another right triangle sitting right here, and it has base c minus x, height h, hypotenuse a. So the Pythagorean theorem for it would say c minus x squared, the square of the first leg plus the square of the second leg, which is this height of this perpendicular, equals the square of the hypotenuse. And each of these can be solved for h squared. So I can subtract x squared from both sides here. B squared minus x squared equals h squared. And here I get h squared equals a squared. And then I subtract this piece off of both sides, c minus x quantity squared. And now I have them both equal to the same height squared, which means I can set this equal to this by the transitive property of equality. So b minus x squared, b squared minus x squared is going to equal a squared minus, I'm going to reverse the order just so that I have it. I'm going to put the a on the left side just so that we're matching this, because I know people like it to match up. So I'm going to put the a squared minus c minus x quantity squared on the left, equaling the b minus x squared, b squared minus x squared on the right. And the formulation that we have here has the a squared isolated. So let's isolate the a squared by adding the c minus x squared to both sides. So we get b squared minus x squared plus a c minus x quantity squared, and this is going to be an a squared sitting here, equals b squared minus x squared. Now square this binomial out, which is going to give us a c times c is c squared. We're going to get c times minus x is minus cx 2 times, so we're going to get minus 2cx. And minus x times minus x is going to give us a plus x squared. And then I want to see here that the minus x squared plus x squared will equal 0. So I can clean those out. So now I have an a squared equaling b squared plus c squared, which is looking exactly like what we have on the front part. The second part's a little bit different. We have minus 2cx, so it's starting to look good, but I've got this x thing messing me up. But if I come back up to this, I see that x is the side adjacent the angle A on this right triangle. So according to right triangle trigonometry, the cosine of the angle A is going to equal the side adjacent the angle A over the hypotenuse. And then if I multiply both sides by b, I get that x can be replaced with b times the cosine of a. So I step down here and I replace x with b times the cosine of a. And these can be interchanged by the commutative property of multiplication. So I can rewrite it as a squared equals b squared plus c squared minus 2bc times the cosine of angle A, which is exactly this case right here. The other two cases we would do the same way. We would just do them with respect to b and c and drop whichever perpendicular we needed to pull it off. Again, in the homework I'm going to ask you to derive it for the case where theta is the angle that you know and you're trying to get s sub 3 squared equal to the stuff. In other words, verifying law of cosines from this perspective in the obtuse angle case. And my tip is going to be, when you label this triangle out, give this distance right here a name, and then use it in a way similar to how I used it over here when I gave it an unknown length a name.